Okay, here we go into chapter 2. I've made each of these videos 10 minutes, so we'll get how far we can get and then move onward. So, elements. These are what you see on the periodic table. They're a pure substance that cannot be broken down into similar substance for a chemical reaction. They can be broken into protons, neutrons, electrons, but they don't have the same properties. So each symbol is identified as a 1 or 2 letter symbol. You can see here titanium is 2-letter. The first letter is always capital L, lowercase for the second letter. If it's just one element, it's our 1 letter to represent the element like this, yttrium. It is a capital Y. All right? The position on the periodic table tells much about the properties that the elements have. We'll talk more about those. So, symbols and formulas. Most symbols are based on an element's name and consist of a single capital letter or a capital letter followed by a lowercase letter, not just a smaller capital letter. That's really important. It has to be a lowercase letter. So those of you that write in all caps, you're going to have to change that. So example, here we have helium. Helium would be He, capital H, lowercase e. Lithium, capital I, or capital L, little I. Sodium, Na, and magnesium, Mg. Notice the second letter is lowercase on both. There are 11 symbols that still reference a Latin or German word rather than English word. Take a second and look at your periodic table and see if you can find some of them. I'll put them up here in just a second, so I'm going to give you about 15 seconds. Okay, I know that wasn't really a lot of time, but let's see how many you caught. So sodium, Na, so the Na represents the Latin or German word. Potassium doesn't start with a P, it starts with a K. That's a lot of mistakes are made that way. Iron for ferrous. Silver, Ag, not S. Tungsten, W. Gold, Au. Mercury, Hg. Lead, Pb. Tin, Sn. Antimony, Sb. Copper, Cu. So those are the ones that reference German words. So you can't just look at the beginning of the name of it and guess what it's going to be. So be familiar with those. So here we look at the periodic table and we've got metals, metalloids, and nonmetals. If you would like to, you can outline this area. Do not color it in because we're going to be coloring in for a different thing, but you can outline these areas on your periodic table. So metals basically are the most part of the periodic table. Metalloids divide the metals and the nonmetals, so you need to make sure that you know these metalloids, and there's 7 of them, and know what they are. So it's sort of like a staircase. They call it the staircase, and under the staircase, we assume these down at the bottom are nonmetals because they act more like nonmetals. So again, yellow is nonmetals, and that includes hydrogen because it actually can come and sit right here by helium. So if you want to color that, go ahead and pause the video. If not, we're going to go forward. So elements of the periodic table, the elements in the periodic table are divided into metals, nonmetals, and metalloids, just like we talked about on the previous page. So what are some properties of metals? Well, metals for the most part are located on the left side of the periodic table. They were in the gray area. They are good conductors of heat and electricity. They are usually shiny, and at room temperature, except for mercury, they're a solid. Mercury at room temperature is a liquid, also known as quicksilver, is what they call it. So here's something called quicksilver, and there's a brand made out of it. That's where it got its name. Nonmetals are usually on the right side of the periodic table. They have a dull appearance, like this. They're poor conductors of heat or electricity. They're also used as insulators. Nonmetals can be solids, liquids, or gases at room temperature. Solids, we have here an example of sulfur and carbon, and a diamond is carbon. Bromine can be a liquid. It goes to a gas very, very readily with just very little heat. And nitrogen, oxygen are gases, and these are the spectrum tubes for those that are filled with those gases and lit up with electricity. The last one we're talking about are the metalloids, this group right here. You'll notice on this table it shows astatine as being part of it. Again, that's They say, some people think astatine should be part of the metalloids, some don't. Your book does not. So just remember the top 6, okay, or 7. These metals are located on the solid line that starts between boron and ends at astatine. The metalloids have properties of intermediate between a metal and a non-metal. And there's only 7 metalloids, and so they're listed right here. So make sure that you're aware of them. Your book now goes into elements that are important to the human body. You could relabel these and go CHON and call it CHON to help you remember what they are. But these 4 elements comprise 96% of your body. So if you look at how it's built up here, others are just part of your head. Everything else is a lot of the rest. They're very important for biological processes, and if you go into 1120, we talk about that in 19 to 22 in the chapters. So my major minerals that are needed in the body are magnesium and sulfur. We need at least 100 milligrams of each of these a day in our daily diet. Magnesium-filled foods can lower your risk of anxiety, depression, heart attack, and more. Some things that are high in sulfur, of course, there are the smelly ones. And then trace elements, we usually need only less than 15 grams of each of these. Iodine is one of them. That is very important. That's needed for thyroid production. There's more than just iodine, but there are many trace elements. So as we look on, focus on the human body, our building blocks are, like I said, CHON is an easy way to remember it, or OCHN. However you want to remember it. That's what makes up 96% of our body mass. And then our major minerals in body fluids are potassium, sodium, and chlorine. So if we're low on those, we're going to have problems. The ones that are found in the muscle are magnesium and sulfur. And the ones that are found in teeth and bones are calcium and phosphorus. Our minor or trace minerals that we only need 0.1 by mass, or about 15 milligrams per day, is arsenic. Believe it or not, we do need arsenic, just not in large quantities because it would kill us. Boron, chromium, same thing with chromium, and cobalt, copper, fluorine, iodine, iron, manganese, molybdenum, nickel, selenium, silicon, and zinc. So when we look at a compound made up of elements, we use subscripts to tell how many of each we have. So in this formula of glucose right here, this is a chemical shorthand for glucose, C6H12O6. The ones in green represent how many of each of the element before it I have. So I have 6 carbons with 12 hydrogens with 6 oxygens. So over here we've got water, H2O, 2 hydrogens with 1 oxygen atom. C3H8 is propane, so we have 3 carbons with 8 hydrogen atoms. So you always write it as a subscript, how many there are. So let's write some example formulas. You try. I'm going to give you a second here. A molecule of sulfuric acid has 2 hydrogens. So what are you going to write? 1 sulfur. What are you going to write? And 4 oxygens molecules. Now, when there's a 1, we don't put the subscript 1. We just put the letter there. So if you put a 1 next to sulfur, get rid of it. You should have come up with this, H2SO4. A molecule of ethyl alcohol has 2 carbons, 6 hydrogen atoms, and 1 oxygen atom. So quickly write this down, what you think it is. 2 carbons, 6 hydrogens, and 1 oxygen. And if you came up with this, you're right. Okay, moving forward. When we have elements, we can draw them many different ways. We can draw them in an expanded form, which is this, also known as stick figure or structural formula. We can do it with models, and this is just a regular model, and this is a space-filled model, or we can write it with chemical formula, or we can write it by its name. So there's many different ways that we can write formulas. We are going to be using this model kit, and we need to be able to know what things are what in the model kit. So nitrogen is blue, chlorine is green, and for most of it, the greens will be chlorine, fluorine, bromine, and iodine, but some of you will have the light yellow, the brown, and the iodine that also have just one hole in them. Hydrogen's always white, carbon's always black, sulfur is a yellow, bright yellow. And phosphorus is sort of a tanny color like that, but it has 5 holes in it, where sulfur should have 6 holes. All right, so going forward, let's look at this, methane. Methane is CH4, so, whoops. So we should be able to write here CH4. Get the pen working, hopefully. And we would draw it with a black in the center. And I'm just going to do the ball and stick model. And we'd have a carbon, or hydrogen, a hydrogen, a hydrogen, and a hydrogen. Now it actually ends up being more like this, where these go back in because it's a 3D model. And this one comes out towards us. So it's more like a pyramid shape. This one right here you should recognize. The whites, remember, are hydrogen. Oxygen is a red. So we have H2O, which we know is water. And then we have CO, so we're going to have a black connected to a red because oxygen is red. And this one is known as carbon monoxide. And we'll learn about how to name them later. We're just practicing here. Hydrogen peroxide is actually H2O2. So we're going to have oxygens in the center that are hooked to each other. And then we're going to have a hydrogen on each end. And the bottom one, BF3, I don't have a tan, so I'm just going to use this with sort of like that. That's my tan. And fluorine, we're going to use green for, so we're going to have a fluorine coming off here, here, and here. Should color those in. And this is named boron trifluoride. Whoops. Helps if you spell it right. Okay, going forward. Given the formula for the following compounds, determine the total number of atoms. So remember that this tells us the exact amount of atoms. We're just going to stop on this page right here, but we're going to finish it. So we have 3 here plus 1 boron plus 3 oxygens. So the total number of atoms here is 7. I'm going to change color so it points out a little bit. Here I've got 1 plus 2 plus 3 plus 2. That will give me 6, 7, 8 total atoms. I should have written atoms at the bottom here because we should keep track of what we're doing. And for perchloric acid, see if you can do it before I do. 1, 1, 3, 5 atoms total. Now, they could ask us, instead of total atoms, how many atoms of chlorine or carbon in any of these, and you should be able to do it. Okay, that's this lecture, and I'll start on the next slide with the next lecture.